Hi everyone. In this lecture, I thought I'll finish the discussion on the leakage compensation circuit that I had introduced in the previous lecture. So again, this is one of the questions I'd post on LinkedIn, and I thought I'll discuss its solution. It's a very simple leakage compensation circuit. Again, I'll not go into the mathematical details in this lecture because I've already discussed how to solve all these parts. What happens to the closed loop and open loop poles once I introduce the leakage compensation circuit, and before and after introducing the leakage compensation circuits in the previous video, I think lecture number 53, AIC Lecture 53. So I'd recommend you watch that. So right now, I'll just talk about this circuit and how does this circuit serve as a leakage cancellation circuit. So if you recall from the previous lecture on leakage cancellation, I said the first thing that you need to do if you want to cancel the leakage current yourself is to estimate it. So you should be able to estimate it and then mirror that current into the main branch. So the circuit will, whatever idea we think of, will contain this two blocks. One is a mirror, a final current source, which is whose gate will be controlled by the cancellation measuring circuit, cancellation current or the leakage current measuring circuit. Okay, so there is a current mirror which will push the current into the output node, and there will be one current or leakage measuring circuitry. So in its simplest form, so to explain this idea, so what I'll do first, conceptually explain what needs to be done, and then we'll see how to arrive at a circuit structure that looks like this. So this is what I need. What I need is, if I can, all I need is a current mirror that can mirror the leakage current that's flowing through the capacitor. So I said the reason why we are choosing 0.1 C is also to save area. So it just has to measure that leakage current and multiply it by a factor of 10. So at that job, I can do by using a current mirror, right? So if you look at this part of the circuit, it's just a current mirror. It's just a PMOS current mirror. It's mirroring whatever current is flowing in this capacitor and multiplying it by a factor of 10. So if I assume this current is 0.1 I leak by 10. So this is going to be I leak. Okay. Now the question is it going to mirror I leak, or who determines what is the current flowing in this capacitor? The current flowing in this capacitor is determined by the voltage across it. So let's call that voltage as VC. Let the supply voltage of this current mirror be Vx. Then the capacitor voltage is simply given by Vx minus VGS. Okay, it's Vx minus 1 VSG. It's actually VSG. So let me write mod VGS. So it's VSG of PMOS or mod VGS. Now that voltage should exactly be equal to V0. For the circuit to, if you want to accurately estimate the leakage current, you have to ensure that the voltage in the replica or the leakage measuring circuit should also be very similar to the main circuit. So if this node voltage is V0, you also have to ensure that this output voltage VC equals V0. So I'll equate this to V0. And that gives me the supply voltage of this current mirror, and that happens to be VGS plus V0. So this is how I thought. When I came up with this idea, it was very, again, it's a student idea. It's very simple. All I needed to do was think of a current mirror structure, and that current mirror should be able to mirror a current in a leaky capacitor. Okay, and then of course with some appropriate current mirroring ratio. The only problem was, how do I decide what the supply voltage of this current mirror? If I just use whatever supply voltage, then the voltage across the capacitor is going to be that supply voltage Vx minus mod VGS. So you have to carefully choose the supply voltage if you want to use this current mirror based cancellation. Okay, so we have to choose the supply voltage carefully. So the supply voltage in this case turns out to be V0 plus 1 VGS. So whatever V0 voltage is, it's the DC voltage of V0. So let me write V0 DC. I have to add 1 VGS to it and then use it as a supply. Now we know, if you have done any basic course on analog integrated circuits, you would know that adding voltage, meaning adding a fixed voltage of value VGS, amounts to just level shifting, right? So level shifting can be easily accomplished using a common drain amplifier. So here I've used a PMOS common drain amplifier because we have to shift the DC level upward If I want to shift the DC level downward, I have to use an NMOS level shifter. So all I need to do is just level shift it by VGS, and that can be accomplished by using a PMOS common drain amplifier. Now, one point to keep in mind here is that the VGS of this MOS here and this MOS don't have to match exactly. Even if you're off by a few millivolts, we are still fine. We are able to, estimate the leakage current to a good extent. Even if I'm able to cancel it by 90%, that's still a good enough cancellation. So I don't have to exactly, ideally for this circuit to work perfectly, I have to ensure that this current source here should be exactly equal to 0.1 times I leak. If I do that, then I can expect Vx should be exactly equal to mod VGS plus V naught, and this mod VGS will be exactly equal to the current mirrors mod VGS. Okay, so remember this device is carrying a current of 0.1 times I leak. So this device here, and if I ensure that the same current is flowing in another PMOS and I chose the similar dimensions for this MOSFET, then I'll end up getting the same VGS for this MOSFET. So this will be same mod VGS. Okay, so plus and minus. Then all I need to do is, now that I have this voltage available with me, I can directly connect it with a current mirror. But there is a problem. I can't directly connect this to a current mirror because this current mirror will act like a load for a common drain, for this common drain amplifier. So which means instead of this current flowing through this MOSFET, this current will end up flowing into the current mirror. So it won't be able to, you can't directly drive it, or we'll see eventually what are the conditions to drive it. Okay, so you should be, for you to directly drive this, it is difficult because the current mirror is going to load it. When I say load, what it means is that you are going to draw some finite current. If you draw some finite current, then this VGS will decrease, mod VGS will decrease. So you don't want that. So to resolve that, I just have to introduce a voltage buffer. An ideal voltage buffer can be realized using an op-amp. An ideal voltage buffer whose input DC and output DC will exactly be the same. I mean, you take an op-amp, connect its output to the inverting terminal, you have a voltage follower. Okay, this is the circuit which I'm going to use. If I use this, then whatever be the current that is demanded by this current mirror structure. So the current mirror structure will demand a total current of I leak has to flow in the mirroring arm, and 0.1 I leak has to flow in the current measuring arm. So total current it has to supply is 1.1 I leak, and this current will keep changing with temperature. Okay, so and that current for 1.1 times I leak has to come from the voltage buffer. So you have to design, if you have to design the voltage buffer, you will keep in mind that it has to at least supply this current. So you'll do some estimations on schematic simulations and figure out what is the leakage current that it's going to draw, and then add some margin to it. So that's how you'll decide the current for this voltage buffer, the bias current for the voltage buffer. Okay, so then this is a circuit that will work perfectly. Okay, so you need to inject the leakage accurately. So you have to ensure the voltage across this capacitor is same as V naught. And to do that, we are using, since it's a current mirror structure, to do that, all I need to do is ensure the supply voltage is 1 VGS plus V naught. Okay, so then you can ensure you get same voltage, the voltage of across the capacitor will be V naught itself. I'm writing VGS here, so please understand it's mod VGS, it's the VGS of a PMOS device. So it's mod VGS, it goes without saying. So that you ensure that the voltage across this 0.1 C cap is also V naught. So that's what we have to ensure that, because otherwise your leakage estimation will not be accurate. Now, can you get away with this buffer? Can I directly connect this? So previously I said they will have loading effect, but can I directly connect it? I mean, this is again something that follows from basic circuit design. Yes, you can connect it directly also, because if you recall from our previous lectures, a common drain amplifier, I said, can be modeled like a voltage source with a finite source impedance. Okay, with a voltage source, and the finite source impedance happens to be 1 over G. Now all you need to do is see the looking in impedance on this side, and ensure that this 1 by Gm should be smaller than the looking in impedance. If you ensure that, then there will be no loading effect. Or said otherwise, all you need to do is just keep increasing this current, choose this current I so large that it is much greater than 1.1 I leak. Okay, so this current is going to be 1.1 I leak. So your current I has to supply that as well, because there is no buffer to supply it right now. So that current has to come from this path. Okay, so that's the only path from supply to the circuits here. So therefore this current has to come, and that current has to be then supported by this current source. So this current source I has to be greater than 1.1 I leak, plus you should also add 0.1 I leak in flowing through this guy. So totally it has to be greater than 1.2 I leak. Your I has to be greater than 1.2 I leak, and again this is something you estimate from simulations. You find through simulations what is the peak leakage current across corners, across peak temperatures, and then choose your bias current I. Okay, here the problem with this approach is that you end up wasting current. So if you recall, if you go back to the previous lecture, I don't end up wasting current there, because the negative feedback takes care of ensuring the voltage across the capacitor is V naught. So it will adjust. So if you just to quickly refresh your memory, so the circuit looks something like this. You have a PMOS device. So here if you see that this is connected to the supply voltage and this is 0.1 C, the current flowing here is 0.1 times I leak. Now here for this circuit to work, I have to over design it across corners, because this circuit, this current I, unless it's a fixed current source, unless you have some process tracking and all that, otherwise if you are going to go for a simple design, I'd keep my current source fixed. So then for safety, to ensure its operational accuracy across corners, all you need to do is ensure that this I is much greater or greater than 1.2 I leak across temperature in device corners. If you ensure that on simulations and pick that current as your DC bias current, then you are good to go. The circuit is going to work. But the problem with this approach is, let's say you're operating in typical corner where you may not be drawing out such high currents. Okay, then all that remaining current will flow through this PMOS, and of course this VGS will be slightly higher, but the problem is you're wasting current. In this approach, where you are using negative feedback to ensure this node voltage is same as V naught, if you're using negative feedback to ensure it, then the current in this PMOS device is varied. That's a variable current. And that variable current, because your gate voltage is free to move there. Okay, so this amplifier will decide what that gate voltage will be, and it's a variable current. So the current drawn from the supply is going to be 1.1 times I leak. Remember, this number is a process and temperature dependent number, and so it will vary. Okay, but that current, I mean, there is no, we are not wasting any extra current here. Okay, that the negative feedback takes care of tracking this current across corners. But that doesn't happen in this circuit. But the positive side is it's much simpler. There is no negative feedback here. The moment I said that there is, of course, there is an advantage of current saving here. But the moment you introduce negative feedback, you have to worry about stability. So there is a stability problem in this loop, right? So you have an amplifier A, another amplifier. This is a common source amplifier. So you have a two-stage amplifier with high gain. So therefore, whenever you have two-stage amplifiers, you have to worry about compensating them. So you may have to end up adding some compensation capacitor. So that will take up some additional area. So that's the problem with using this approach of negative feedback, is that you have to keep in mind that you have to compensate the loop, the negative feedback loop. On the other hand, you don't have to worry about the compensation problem in this method of implementing the circuit, but you end up wasting current because you have to over design it. You have to ensure that this bias, because this bias current I is constant, you have to ensure that this bias current I is chosen in such a way so that the circuit will work even in the extreme corners when your leakage current is maximum. So typically it happens to be in fast and hot corners. Okay, even the circuit has to work even in those extreme corners. So you'll pick this I to be greater than those extreme values. So let me write I should be greater than 1.2 I leak max. So how do you compute this I leak max? This is something, a value you estimate from simulations. So the power dissipation in the circuit is going to be this much, 1.2 I leak max times VDD. On the other hand, in this circuit, if you use a negative feedback, the power dissipation is going to be, of course, you have to include the amplifier's power or the error amplifier's power dissipation as well. So that power dissipation is going to be 1.1 I leak plus I amplifier. But remember, this 1.1 I leak is a current which is tracking with process, so there is no max there. It's not max of I leak, so you will be saving some power. Okay, so that's the advantage of using negative feedback, but the disadvantage is stability. So an analog circuit is very common. You will always end up having trade-offs. So one idea might look better, but very rarely you will have some ideas which will be really good, then we end up choosing that one. Okay, sometimes you'll have two equally good ideas, then you see what's more suited for your application. If you're crunched in terms of area, crunched in terms of area, then maybe if I use compensation and all that, negative feedback approach may not be good. Okay, even though I'm saving in terms of power, I'm maybe blowing up area there, so maybe it's not the best idea. So then we may come back to, even though current is higher, it's much simpler. It just requires one extra MOS device. Okay, so and one current source, so it's much simpler in implementation, not much in terms of area. Power, let's say your application doesn't care about power, so then you can go ahead with that. Okay, but in an application where you're power sensitive, not area sensitive, then maybe you can end up choosing this application. Okay, so that's it. So that's the second idea that I discussed. In fact, this is the question I posed first. Okay, it might look a bit complicated, but if you just reduce it to its fundamental constituents, it's a very simple idea. The whole idea reduces to very simple. All I had to do was design a current mirror. So that's how I thought of this idea. I said, okay, I just need a current mirror which has to measure this current and inject into the main capacitor. So then the next thought process is what should be will that current mirror ensure the voltage across this, the replica capacitor exactly equal to V0? Then if I have to ensure it to be V0, what should I do? So that was my thought process, and this circuit was the outcome of that thought process. The second thing that you have to ensure is this circuit will also need a larger VDD. The supply voltage here, so if V0 is the output DC voltage, V0 plus 1 VGS is the voltage at this node. So that will be V0 DC plus 1 mod VGS. Now VGS is actually 1 VT plus some extra override that can be a very large voltage in low voltage technologies. That plus the voltage that you need to keep this current source in saturation will be the minimum supply voltage needed. So your supply voltage has to be V output DC plus 1 mod VSGP, which is greater than VT mod VTP, and a bias voltage necessary to keep the current source in saturation region. Okay, so which I've called VISRC. This should be your minimum supply voltage. So there is another supply voltage constraint as well in this idea. Okay, so the way I thought where I was working, where I was thinking this idea, where it could go into a PLL, it turned out that the output voltage was always at mid rail. It was always at VDD by 2. So I had enough margin, so I could think of an idea like this. Okay, else if I did not have margin, then going for negative feedback approach is a better solution. Okay, so that's it. I've just discussed this idea, and the remaining parts of this question, which is what happens to open loop, closed loop poles, the same things which we discussed in the previous lecture will also hold true there as well. So you don't need to rework it here. The similar things, like once I introduce the leakage cancellation circuit, it will also act like a negative resistance. Even in this approach, it will act like a negative resistance, and it will cancel out the low frequency pole and push it to DC. Okay, it will cancel out the positive resistance and push the low frequency pole to DC. So all those things will happen. So part A and part B, I have just discussed how to solve approach part C and part D of the question. Okay, thank you.